welcome back to my channel, and today I'm going to be talking about linearity and an introduction to quantum mechanics. So let's begin. So what is linearity? Well, why is linearity important? Because when learning a subject, we need to know why it's important before we learn what it is. Well, linearity is important, especially to quantum mechanics, because in quantum mechanics, if we know that the theory is linear, which it is, which we can demonstrate new solutions that is very easy to create. And this may not seem that theoretical to you and that more capable of understanding, but it will. So let's now talk about linearity. So linearity, what is this linearity? So what is linearity? So that's a good question. So linearity is not something which we have about a line. When we have a line, that's something different. But linearity is a little different than this because it's dealing with solutions. So linearity just states we have a dynamical variable. Dynamical variable. So we have a dynamical variable, which we can just write over here. And then now let's describe the definition. So when we have a solution and another solution, we can combine them to get a new solution. Okay, so this is just a few words and we can understand this. So what does this mean? Well, we have the concept of linearity. So when we have a solution and another solution, we can combine them to get a new solution. So you may be wondering, first of all, how do we have multiple solutions? Well, when dealing with high advanced mathematics and physics, we can have lots of solutions. For example, if we have, let's say, the integral of 5x raised to the power of 4, which if we take it dynamically, we'll get x raised to the power of 5, and then if we just input random values, the answer will change. So that's like typically each solution. And it's stating that if a theory is linear, we can make more solutions and get a more profitable experience, because if we get more solutions, this can reduce all our work. So how does this relate to physics? Well, we'll see that in a moment. So what is a dynamical variable? Well, a dynamical variable is the main variable. The main variable means the variable that is changing. We can have more than one dynamical variables. For example, we can have U as our dynamical variable, A, R, C, any letter of the alphabet. We can even have more than that. So a dynamical variable is just a variable that changes, and it's called the main variable. So now let's look at the laws of linearity. So you might be wondering, I thought linearity was just about some few words, but actually it has some laws. So linearity is described as a linear operator. Why? What's an operator? Imagine we have addition, subtraction, multiplication, and division. So we can write it over here. So we have addition, subtraction, multiplication, and division. So these are our three, and then four things we use. Multiplication is just a negative and division is just a 1. So technically we can just call it 2, but we can write it 4. So let's just say we have the 4 operators which we usually use. Like 1 plus 1 is 2, 1 divided by 1 is 1, 1 times 1 is just going to be 1, and 1 minus 1 is 0. So those are our operators which we use. So what about a new operator? Well, what does this operator do? So let's define an operator. What does an operator do? So if we have a specific function added to another function, an operator just does something to that function so we can get another output. So if we have an operator and this function, an operator just operates something on a function. Like you're operating on a human, you're taking like their heart out, putting another heart. You're changing something within. That's what an operator does. It just changes. So what exactly linearity is, it is the linear operator times a dynamical variable u is equal to 0. This is the basic laws of linearity. So linearity just stating that when we have a linear operator, and this operator is just essentially going to equal, this linear operator operates on a specific variable, which turns out to be 0. So this is the concept of linearity. It turns eventually into 0. So what does this linear operator do? Imagine we have a specific function. Let's say u is going to equal blah, 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 f of blah, blah, blah. What does a linear operator do? Well, a linear operator, let's say this variable is just something. Let's state that it's this thing. When we multiply by the linear operator, what we do is we're just going to make this like this. It's different. As you see, we have something different. For example, the linear operator could be something with differentiation or integration. So linear operator essentially is just something that operates on a variable. So this is the first law of linearity. A linear operator times a dynamical variable, which in this case is u, has to equal 0, as an operator operates on a variable to change it. So now that we've got our first law, let's talk about our second law. The linear operator times, let's say we have a u, where a is a constant. Well, this is just a times the linear operator u. So this is kind of reminding us about integration. When we had about integration, we just took the constant that's multiplied out. So that's kind of reminding us about integration. So this is another law. And the third law is when we have multiple dynamical variables. For example, if we have, let's say, L of u1, u2, this is just L of u1, and then L of u2. So technically, this is another of the laws in which we require for linearity. So these essentially are the three laws that are required for linearity. So linearity is pretty much simple. It's just these three laws that we have to define. But now let's go into Introduction to Quantum Mechanics and how this differentiates from other branches of physics, because that's what we're mainly here to do so. So we can erase the definition of linearity, but let's keep the laws. So let's pick the most rivalry subject to quantum mechanics. What is it? Well, I would say the most rival to quantum mechanics would be general, I'll just write it GR, and Einstein's field equations, which are also part of GR, versus quantum mechanics. So these two are the ones which we have to matter about. GR and QM. What's the most distinguishing of them? But let's actually first talk about what QM is. So what is QM? Well, that's essentially just quantum mechanics. But what itself is quantum mechanics? Quantum mechanics is the branch of particle physics. In particle physics, we study particles. Quantum mechanics is just studying the behavior of these particles. We're trying to find the velocity and the position of these particles. Now let's compare that with the other thing. So what's the other thing? Well, let's compare it with biology. So if we use biology, we can technically understand why quantum mechanics is not the main field, particle physics is the main field. So imagine we have biology. Biology is just the whole subject, and we have, let's say, cells. So biology is dealing essentially with cells. And then cells, inside we have the cell behavior. Because in cells we have cell parts, cell behavior, and blah, blah, blah. Quantum mechanics is just the quantum behavior, or the cell behavior, and this thing is the quantum behavior, and the main cell region is just going to be particle physics in our case. So that essentially is why quantum mechanics falls into particle physics. So studying the behavior of position and velocity and many more traits of particles. Now, let's look at what general relativity is. General relativity essentially is just talking about space-time curvature. Imagine if we have a big planet, the big planet curves space-time, which essentially is general relativity and Einstein's field equations. So we will talk about general relativity and Einstein's field equations in another video. So now, let's talk about what QM is and how we can actually use it. So if someone asks you what's the difference between these, you will say probably GR which is general relativity, is just dealing with the big, and QM is dealing with the small. Or you might say GR is space-time curvature, and QM, or quantum mechanics, is just quantum particles behaviors. And if you were to really say it, you would say exactly the definitions of these and see how they're different. But what if someone asks you, mathematically, how are they different? Well, you would say the equations are different. But instead of that, because everyone knows the equations are different for different branches of physics, and even in quantum mechanics, we just don't have one solid equation. We have different equations. So, how does this help into quantum mechanics? Well, this is where linearity comes in. So linearity is a special property that quantum mechanics has. If we have a solution and another solution, well, we can combine them in quantum mechanics and get another solution, which essentially is linearity. This makes our life a lot easier because imagine we're trying to find a specific solution. And that solution, if we find a previous solution before it, we can just combine another solution with it and see if we get that solution. And we can find many solutions which we didn't expect. But general relativity, this is a non-linear theory. So this is why general relativity and Einstein's field equations are harder to calculate than quantum mechanics. Well, if you have the Heisenbergs uncertainty principle, it's pretty easy. But compare the Schrodinger equation with the Einstein's field equations, they're pretty hard. But I would say Einstein's field equations are harder because if we have one solution and another solution, and we can't combine them and get another solution, that other solution may be valid and may not be valid. So that's the difference between general relativity and quantum mechanics. So now that we have covered this, let's talk about the basics of quantum mechanics. So, quantum mechanics, let's talk about the basic equations. And before we do that, let's talk about one linear equation inside quantum mechanics. So the Schrodinger equation essentially is complex variable I, h bar, and then partial derivative of the wave function divided with respect to time. Then we're going to have this is equal to the Hamiltonian, and then the wave function. Okay, so this is just a regular equation, and this is the Schrodinger equation. So the Schrodinger equation is written a lot, and it's written in a lot of ways, but this is the one way I picked it. So, what is so special about this Schrodinger equation of linearity? Well, let's look at this Hamiltonian. This is called the Hamiltonian, which we'll discuss in another video. And this Hamiltonian is very special because this is a linear operator. This is a linear operator, and if we know that this is a linear operator, that makes our life much more easier. We can state that this is linear, but let's see what the linear format is if we use the linear operator itself. So if we were to use it, L, and then our dynamical variable, which is psi, which is going to be psi, or we can else write it as the wave function is equal to the complex variable h bar, and then the partial derivative of the wave function with respect to time subtracted by the Hamiltonian operator and then the wave function. So this will essentially be if we have just the linear and the dynamical variable. If we write it in this format, this is what we get. So someone asks you what's the linear format, you can just say, well, the linear format is essentially this. And we already know that this linear format works, and we know that the Hamiltonian is a linear operator, so we can state that Schrodinger equation is a linear equation. Okay, so why do we subtract this? And we do subtract this because we stated that the linear operator times the dynamical variable, which is u in this specific case, is equal to 0. So if we subtract it, we essentially just get 0. So this is also equal to 0. So now that we've talked basically about the Schrodinger equation, let's talk about one more rule in quantum mechanics, which will deeply interest you. So this rule is the most buzzing rule of quantum mechanics. When you think of quantum mechanics, everyone usually says, hey, this is the rule for quantum mechanics. And they don't really describe the equation, which the equation is really necessary. It transferred all of physics. So let's talk a little bit about the history of quantum physics. The history of quantum physics was mostly developed by lots of people. There were people, for example, like Max Planck, Max Born, Niels Bohr, Erwin Schrodinger, and Werner Heisenberg. But the one we saw before was Schrodinger's equation, and now we're going to be talking about Heisenberg's equation. And there's different interpretations of quantum mechanics, which we'll talk in the next video. So, Heisenberg's equation. What is Heisenberg's equation? Well, Heisenberg's uncertainty principle, as it's called more, is delta x delta p is greater than equal to h bar over 2. So this is essentially our equation, and this is just stating that we cannot find the position and the velocity at the same time, because one of these variables means position and one of them means the velocity. And this is equal to h bar over 2. What is h bar? Well, h bar essentially is just h over 4 pi. So h over 2 pi actually, not 4 pi. And when we do h bar over 2, we can multiply 2 and 2 to get h over 4 pi, which is essentially just the same as that. So this essentially is the Heisenberg's uncertainty principle. So Heisenberg uncertainty principle is the one which we just saw now. So remember when everyone says that we cannot find the position and the velocity of a particle at the same time? Well, if you were to represent the equation, this would be it. We're going to be diving into this equation then in the next video a lot. So stay tuned for the next video. And now we can make this video to a conclusion. If you like this video and if you like this channel, please subscribe to learn more. Thank you.